Hello and welcome. In this video, we will see how to create analog scaling function block in the TI portal by using SCL language. So in the PLC system, we uses analog signal everywhere like pressure, temperature, flow. But PLC don't understand the engineering values which are coming from those sensors. So PLC read only raw values. So in the Siemens, that raw value it is 0 to 27648. So if sensor gives 0 milliamps or 4 milliamps, we will be getting 0, and if it is giving full value, that is 20 milliamps or 5 volt or 10 volt, then we will be getting 27648. So basically the process of converting this raw value into the real value, it is nothing but analog scaling. Now, which formula we have to use to get these real values from the raw value? So, let us see that formula first. So, it is nothing but the line of state equation. Y is equal to mx plus c. So, y is your desired output and x is your raw value side. So, m is nothing but your slope, which can be calculated by y2 minus y1 divided by x2 minus x1. X is your raw value input and c is the intercept point of this our line and y axis. So if we implement this y is equal to mx plus c, we will be getting scaled value. Now let us implement this formula, that is analog scaling, into the TI portal. So here we can use any CPU. So here 1215C we will be using. So here we will not keep any password, we will keep only legacy communication, disable access control and finish. So here, okay, now what we will do, we will add one FB and we will give name analog scale. So here what we will do, so for better understanding, we will write for our desired formula scale value is equal to engineering max minus engineering mean divided by your raw max and raw mean bracket complete. So this is your y is equal to, this is your m is the slope, that is engineering max minus engineering mean divided by raw max minus raw mean, multiply by your raw input minus raw minimum. So this is x, and your c is the engineering mean. Okay, now simply we have to implement this formula. Now what we will do, here we require to give input, that is raw. So data type here it will be integer, engineering max here we want it in real, engineering mean. So engineering max and engineering mean is nothing but your scale max and scale mean. Raw max, raw mean. So these are the input, and in the output we will use scaled value, data type real. Now simply we can implement this formula. So here scale value is equal to engineering max minus engineering mean divided by raw max minus raw mean. So in the Siemens usually this raw max value is 27648 and 0.0. Okay, so here raw input minus raw mean here bracket complete and plus your engineering mean close. Now here our raw is in integer format and raw minimum is real. So here we have to convert integer to real, and here is the so here one more variable we would be required. So here we can use temporary variable as well as static variable, but if we are using static variable, it will be coming in every instance of the FB, and if you are using temporary variable, then it will not be coming in the every instance of this particular FB, and the value of that particular temporary variable, it will not be retained in the next scan cycle. So here we will use temporary scaled value, and the value of this raw, it will be copied to it should be temporary raw value, and the temporary raw value okay. So here we have to use double colon. Okay, so now this formula is ready. So if you call this function, and if you put this engineering maximum value and engineering minimum value, so by default here we have copied this 27648 in the raw max and raw min. So we will start getting the scaled value. So this is very basic analog scaling block. So here if we want to check it, we will call one simulation instance, and we will download it. Is taking some time, so let us wait. So simply download Okay, now this block is also ready. What we will do, we will call this block. So analog scale dB 1, and here we will add one database also. So here real 1 engineering max scale value, and also here we will raw data type is integer. Now we will connect raw engineering max engineering mean. So this 27648 and 0, it is already there, which is raw maximum and raw minimum. So scale value is so we will download this block and we will check it. So now let's say our engineering minimum is 0 and engineering maximum is 150 degrees centigrade, that is temperature sensor. So now if we get exactly half value, that is so we are almost getting 50%. So if we change it to 60,000, we'll be getting 63. If we will be going to 27648, that is maximum, so we should get 150. 2764 27647. See here we have engineering minimum, it is 0, and engineering maximum, it is 150. So 27648 150. If we force half value, so 271313825, that is no 825, that is 50% of full range. If we reduce it, 35, and if we make it 0, it will give 0. If we make it 27648, it should give 150. Okay, so this is the basic scaling function block. Now here what we can do, we can add some functionalities like error detection, like simulation or alarm handling in this block itself, so that it will make our code standardized and efficient, so that you can call this simple block and you can use it for analog scaling, error detection or alarm generation. So here what we will do, we will add some functionalities. So here what we will do, temp scale value so if this temp so here how to detect error, if your temp raw value is greater than raw mean and temp raw value is less than raw max, then our we will take one output, boolean output, that is error. Then error should be false. That means whenever your raw value it is greater than your raw minimum and it is less than raw maximum, that is your raw value when it is in the range, then error should be false. Else if your raw value is less than 0 or raw value 0.0 and if your raw value is greater than, let us say, 3000, then error set to true. Now, when this error will be true, when our raw value, if it is raw, if the raw value is less than 0, or if the raw value is greater than 3000, so our normal range is 27648. So when these two conditions will appear, when your wires of the sensor are short circuited, or if it is open circuited, then our true bit it will be true, so that operator will come to know that sensor there is a instrument error. Okay, so this kind of error detection we can add. So apart from this error detection, we can use simulation. Now let's say if maintenance engineer he want to check the sensor, or if process engineer he want to check the sensor, but he don't want to run the system, so in that condition he can use the simulation mode, so that he can simulate the sensor value to any desired value. So here we have to add one input, simulation value, and simulation enable. So for software engineer also it will be useful to check the programming by using this simulation. If simulation is enable, now here one more condition is there. If process engineer or if customer, if he intentionally put greater than engineering maximum or less than engineering maximum, then we can code like this: if simulation value is, if user put greater than engineering maximum, then this temp engineering maximum. If user put simulation value less than engineering minimum, then engineering minimum else here it should be simulation value. End if and both end if closed. Okay, so here if not error and not simulation enable, then scaled value is equal to this guy. So this is our scaled value, but it is we have stored it in temporary variable. So we are copying this temporary variable value into the scaled value output. When there is a no output, when there is a no error and no simulation enable. So if simulation if error is there, then okay, so if simulation is off, okay, now here error. Okay, so here what we can do, when no, we have to use this one. When so this is the error condition. Already we have got this error bit. So here raw mean, when temporary raw value, then our scaled value it should be engineering minimum else if again the simulation is off and if temporary raw value is greater than the max. So our output it should show. So when our raw value is less than raw minimum, then our scaled value it will show engineering minimum value, and if raw value is greater than raw max, that is 27, when the value is greater than 27648, then the scaled value it will not show beyond the engineering max, it will show up to engineering max only. And we will finish this loop. Okay, so here also, here what you can do, we can add alarm conditions or alarm handling also. So here I will show you how to add alarm, how to add two alarms, that is high set point, high enable, low set point, low enable, and alarm acknowledgement. So here high alarm, low alarm. So here you can add the alarm bits for the respective alarm. So here we are taking only two alarms. So if high alarm enable and scaled value is greater than high SP, then your high alarm it will set to true. If low enable and scaled value is less than low SP, then our low alarm will set to true. Loop close. If ACK, if acknowledge, then this both the bits we can make it false. So here so as per alarm requirement we can modify this particular logic. So when a user wants acknowledge this alarm, so when he want to reset this particular alarm, so based on that we can modify this alarm. So here we are implementing formula, so we are taking the values of we are calculating the values of this y is equal to mx plus c, and we are taking it that value in the this temporary variable. Here we are detecting the error whether the raw value is greater than raw max or raw min. So based on that, error bit is also triggered here. Here we have added simulation functionality, and here we are putting the actual value, whatever the scaled temporary scaled value, into the scaled value when there is no error and no simulation. When there is no simulation, and if raw value is greater, if it is less than raw minimum, then engineering minimum, it will be copied to raw, it will be copied to scaled value, and if it is greater than raw max, then engineering max, it will be copied to scaled value. So if the range is 0 to 150 degree, and if the physical values, that is the raw value, if it goes beyond 27648, then this loop will, then this part of the code, it will be enabled, and engineering max, that is 150 degree, it will be copied to scaled value. So operator will not get confused. For if the range is 150 degree and why the sensor is showing greater than 150 degree, so for this thing we have implemented this. So here we are handling alarm. So now, so apart from this, if you required any other functionality like offset, you can add. If you want to add offset, you can add offset. Offset means, so after some time, if sensor deviates from the expected value, so now let's say if the temperature range is 0 to 150 degree, but after some physical condition, climatic condition, if it is showing 0 to 151 or 0 to 149, so this offset, it will help us to show the correct value. So here we can add offset. So when the sensor is out of calibration, it will be useful. So like this, you can add the required functionality. So we will download it, and we will check this block. So here in the sim enable sim value HSP high alarm enable LSP, that is set point for low alarm, low enable. So this thing we required it bull. Also we will add offset. So not every time every functionality will be used, but it will save your time when customer asks us to develop particular functionality. So simulation value, simulation enable, HSP high alarm enable, LSP low enable. Here we will add offset, and also we will add acknowledge. So anyway, acknowledge data type we have to show, we have to look here. So here I think boolean data type. Yes. So in this way we can create a scaling block. So here what we'll do, we will check it. So it is downloaded successfully, and now let us go to the monitor. Now PLC is in run mode. So here we will set value 150 and we will force the 50% value. So here what we will do, we will check the simulation. So if simulation, so why this simulation is not working here? So let us check it. Hmm. Okay. So here we have not passed this particular value. Elsif, or here we can pass this value here itself. So this will be true only in simulation, and this part is separate, this part is separate. Okay. Now this block, it should work correctly. Okay, so here we will change the simulation to 15. It is 15, and we will change it to 100 degree. It is 100 degree, and if we make it disable, it will take the original value from the sensor. So if we force the raw value beyond limit, it is not beyond limit. Now here we will force. Okay, so the value is greater than 27648. The scaled value, it will show 150 degree. Here error will show true. So we can generate particular alarm, or we can make that particular data link red flashing, or it based on the animation. And if we make it -2, that is also, error is also getting true. So again it comes to normal. Here again we will force the simulation, this raw value to 13,000. So it will show 70 degree. If the temperature goes beyond 75 degree, it should give the alarm. We will make it enable, and we will make it 14,000. See, high alarm is true. Again we will take it back. We will acknowledge. So once acknowledged, that alarm goes to 0. Again we will make low enable, and we give the set point 10 degree. So if the temperature comes below 10 degree, it should give alarm. So 32, and here we will give 600 count. So 3, and low alarm is enabled. So in this way we can use the analog scaling block. So here we have converted, here we have calculated the basic formula. Here we have converted the integer to the real here. So this thing is temporary calculated value. Here we are detecting error. This is simulation. So here we are moving the values. So alarm handling. So in this way we can use this analog scaling block. If you like the video, please like, share and subscribe. Thank you.